Hi everyone. In this talk, I will discuss the so-called Fishnet theory, which may be seen as a minimal model for conformal field theory in 4 dimensions. It was discovered only 5 years ago, and it is a non-supersymmetric and also non-unitary CFT defined by an extremely simple Lagrangian. It is expected that this theory can be solved exactly. For instance, in these plots, it's shown part of the spectrum of conformal dimensions as functions of the coupling constant. You can see from the pictures that there are branch points, and the scaling dimensions can become complex, which is a sign that the model is non-unitary. While the plots are very complicated and are not described by any simple formula, the whole spectrum is computable exactly. I will explain how one can do that and present some perspective on the computation of more complicated observables. The solvability of this model comes from two properties. First, as we will see, the Lagrangian of the model generates only a special class of Feynman graphs with the structure of a regular lattice. These diagrams are called Fishnet diagrams. Moreover, these graphs encode a special mathematical structure known as integrability. We will encounter Feynman diagrams with this structure. They are built as a square lattice of massless boson propagators in 4D. This network is generated iterating a graph-building operator, which will play an important role. It is an integral operator because we need to integrate over the vertices, which carries us from one row to the next. The property of integrability descends from the validity of an algebraic relation known as the Yang-Baxter equation. I will not try to be detailed, however, it is illustrated in a picture and it comes from an integral identity called the star triangle relation. This relation has an important consequence. It implies that the graph-building operator, with appropriate boundary conditions, can be embedded into a one-parameter family of more general operators called transfer matrices. And the transfer matrices commute non-trivially for different values of the parameter. This parameter will be called the spectral parameter. This commutativity property means that there are many integrals of motion commuting with the Hamiltonian, which is the usual definition of integrability. We will see that this mathematical structure gives us a lot of special tools to study the model. The integrability properties of some types of Fishnet diagrams were in fact known since a paper of Zamolodchikov in 1980. At the time, these diagrams were just considered as an interesting subset of all possible planar diagrams. It was not expected that they could be the only type of diagrams appearing in a consistent model. Zamolodchikov showed for the first time that integrability could be found at the level of a Feynman diagram, and classified the three types of integrable Fishnet graphs built with massless bosonic propagators. The integrable Fishnet number 1 is the square lattice in 4 dimensions, which we have just seen. We now know that these diagrams describe completely a consistent theory, the Fishnet model I'm focusing on in this talk. As I will discuss shortly, the Lagrangian for this theory was constructed by Gurdogan and Kazakov as a particular extreme deformation of n equals 4 Super-Yang-Mills theory. The integrable Fishnet number 2 is a triangular lattice, but now made of propagators living in 3 dimensions. Also, these diagrams describe a non-unitary CFT, which was obtained as a deformation of another superconformal model, ABJM theory, by Caetano Gurdogan and Kazakov. The integrable Fishnet number 3 is the hexagonal lattice of propagators living in 6 dimensions. Mamrood and Torrent have proposed a Lagrangian for a consistent CFT described by these graphs. It is still a mystery if this theory can be seen as a deformation of a superconformal model like it happens in 4D and 3D. Let's come back to the 4-dimensional Fishnet model and see how it was constructed. Gurdogan and Kazakov started from the gamma deformation of n equals 4 Super-Yang-Mills theory. This deformation depends on 3 parameters gamma I, which in general completely break supersymmetry while preserving conformal invariance. The parameters enter explicitly the Lagrangian as phases. it was shown that double trace counterterms are also needed for conformality at the quantum level. The double trace couplings are in general complex, making the theory non-unitary even for real values of the gamma deformation parameters. In the following, we will ignore the double trace terms. They are present also in the Fishnet model, but they enter only some special processes and do not play a role in what I will discuss. The double scaling limit considered by Kazakov and Gurdogan sends some of the gamma phases to infinity in an imaginary direction. This breaks unitarity even more drastically. At the same time, the Young-Mills coupling constant is scaled to zero in such a way that some new effective couplings are kept finite. This limit kills most interaction terms in the Lagrangian, in particular all the interaction terms involving gluons, because the Young-Mills coupling goes to zero. The only terms that can survive are the ones multiplying the phase factors that scale to infinity. So apart from free gluons, we end up with a much simpler Lagrangian with only matter fields. The simplest case is the one where we scale to infinity only the phase gamma 3. This gives the Lagrangian of the biscalar Fishnet model, a theory of two complex scalar fields surviving out of the three complex scalars of n equals 4 super Young-Mills. These fields are n by n matrices, and there is now a global UN symmetry, which is a relic of the gauge group, and two U1 symmetries associated with the two scalars. Let's represent the two scalar propagators with black and red directed lines. Non-unitarity implies that while this interaction vertex is present, this one is not. This rule is essential for conformal invariance. For instance, it forbids the London Underground diagram, which would give mass to the scalars. In addition, many more diagrams which would be present in a standard phi to the 4 theory are also not allowed. The net result is that only graphs that have a Fishnet structure in the bulk are present in this theory. These are examples of Feynman diagrams built with these rules. They are constructed by iterating many times either wheels or spirals. This means that for any loop order, there is at most a single Feynman diagram, which is amazingly simple. Now let's see how integrability can help us to solve the model focusing on the Lagrangian limit. By solving the theory, we usually mean computing all correlation functions. The two-point functions are the simplest objects and are fixed in terms of the conformal dimensions delta. I will first discuss how to compute the spectrum of conformal dimensions, which is well understood, and at the end I will relate it to the much harder open problem of computing general correlators. The Lagrangian limit is dominated by single trace operators, so we will focus on these ones. For simplicity, I will consider only operators with one type of U1 charge, which take this form. The dots imply the presence of quantum corrections. There is a nice way to determine the spectrum using a concept introduced in a paper of Kolya and Amit Sever called the CFT wave function. The wave function is defined as a correlator between the single trace operator we want to study and a second trace where the fields are point splitted. By definition, this is already a renormalized correlator at the non-perturbative level, and it contains information on the exact value of delta. To compute it from diagrams, we would need to resum infinitely many wheel diagrams and renormalize the operator to remove the UV divergence at the point x0. However, there is a shortcut. Because the diagrams form an infinite ladder, adding one more wheel should leave the wave function unchanged. This gives an exact Schwinger-Dyson equation for the wave function, which can be seen as a Schrödinger equation where the Hamiltonian represents the graph-building operator adding one wheel and the eigenvalue is 1. For convenience, here we separate the coupling out of the definition of the graph-building operator H. To find the conformal dimension delta, we need to first diagonalize the graph-building operator treating delta as a parameter, and second, impose that the eigenvalue multiplied by the coupling should give 1. If we had access to the eigenvalues as a function of delta, we could invert this relation and compute the scaling dimensions as a function of the coupling. As we saw, the Hamiltonian has a special property of integrability, So how does this help us to diagonalize it? In some simple integrable models, there is a direct way to construct eigenfunctions through the famous beta ansatz, but for technical reasons, we cannot apply this method here. However, a more general consequence of integrability is the property of separation of variables. It is expected that there should be a special set of coordinates where the eigenfunctions take a factorized form, written here schematically. The factors are the so-called Q functions. Now the diagonalization problem, which was a many-body problem for J spacetime variables, can be reduced to one equation in just one variable for each Q function. The Schrödinger equation rewritten for the Q functions is called the Baxter equation or quantum spectral curve. For the Fishnet model, at the moment we do not know how to construct the basis where the wave functions are factorized. It is possible that this will be achieved in the near future because a lot of new technology related to the separation of variables is being developed. However, what we already know is the form of the Baxter equations. This is thanks to the fact that they share a common structure in many integrable models, which involves the commuting transfer matrices I mentioned at the beginning of the talk. The precise form of the Baxter equations for general operators in the Fishnet model was deduced by Kolya and Amit. Here I am omitting some details, but importantly, the T functions are the eigenvalues of the transfer matrices and they are polynomials in the spectral parameter. The coefficients of these polynomials are eigenvalues of the integrals of motion commuting with the Hamiltonian, and one of them is the eigenvalue of the Hamiltonian itself. To fix the values of the integrals of motion, one needs, just as in any Schrödinger equation, to impose a quantization condition. Here, first we look for solutions for the Q functions with a given asymptotics at infinity. This is where delta enters the problem. And then the quantization condition is the requirement that some integrals involving products of Q functions should be convergent. The integrals go around the infinitely many poles of the Q functions. This condition was found in a different form in papers by myself, Kolya, David, and others. The form I presented here, which involves an integral, is similar to the usual quantization condition for a Schrödinger equation, where the wave function should be normalizable. In fact, these integrals over the Q functions are really related to the norm of the state, and they also appear in the computation of some more general observables. I can tell you more about this during the discussion. One can efficiently solve the Baxter equation and impose the quantization condition numerically. This is the method that was used to generate the spectra I showed at the beginning of the video. This discussion can be generalized from local operators to the case of non-local operators realized as cusps in Wilson lines. The relevant diagrams in that case are fishnets attached to two lines forming a cusp. The Fishnet model has no gluons, so it may seem strange to use this kind of boundary conditions. However, one can show that these diagrams arise in a well-defined limit from legitimate cusped Wilson lines in n equals 4 super-M mills. These observables are also interesting as a laboratory to develop new integrability techniques. The Baxter equation describing the full spectrum of these Fishnet cusps was obtained recently in a paper to appear of Julius, Kolya, and Niccolò. So now that we know the spectrum, how do we compute correlation functions? This is an open problem which is very difficult both in this theory and of course in n equals 4 super-M mills. In the latter model, which is more complicated, it is actually difficult to even formulate precisely this problem in the language of integrability. In the Fishnet model, however, this is much more transparent. We can interpret the computation of correlation functions as the problem of gluing wave functions together. For instance, a three-point function of single trace operators can be obtained by gluing together three wave functions as shown here. In this theory, the gluing is by simple tree-level propagators, and all the interesting coupling dependence actually comes from the wave functions themselves. This may seem still very difficult to compute. However, there is growing evidence that once we use the separated coordinates for the wave functions, the correlators should become simple. There is a number of examples of this now, where it was found that correlation functions can be written in terms of some integrals over products of Q functions. The integrals are of the same type that we saw before in the quantization condition, but now the Q functions should come from different operators. In the discussion session, I can tell you a bit more about these results and some ongoing work that we are doing with Kolya and Fyodor Levkovich-Masluk in this direction, and about some possible strategies to draw some lessons for n=4 super-EM mills. So see you at the discussion session. Thanks for listening.